speaker is Christoph Langhammer from Chalmers University of Technology in Gothenburg, Sweden. Christoph is very well known for his works in hydrogen-metal interactions, heterogeneous catalysis, biosensors, gas sensors, covering quite wide range of applications of plasmonics in different areas. And today he's going to talk about microfluidics and plasmonics. Yes, please.
Yes, thank you for the introduction. And indeed, I will talk about something else that I usually talk about. So this is the first that I present this work. But before we go there, let me also sincerely thank the organizers to give me the opportunity to talk about our attempts of integrating nanofluidics with single particle plasmonics. And the outline of my talk is basically that I will start out by motivating at the more general level, not only focused on this particular topic, why it is relevant to look at nanoparticles one at a time. After that, I will try to give you a flavor of our efforts in this direction in two different fields. The first one towards sensing and biosensing, if you wish, and the second one in the field of heterogeneous catalysis on single nanoparticles. So, why single? I think this SEM picture of colloidally synthesized palladium nanoparticles, which were supposed to be single crystalline cubes, pretty much shows it quite drastically. Because fact is that nanoparticles, already at this level, you see the scale bar, but at the atomic level, there is no particle that is exactly the same as another one. So ensembles of nanoparticles will always, by definition, be heterogeneous. Now, why should we worry about that? Well, for example, for many functional nanoparticles, size or shape matters. And one, for me, of the most beautiful examples to illustrate this is this work from Wayne Goodman's group from '98, where they take gold nanoparticles, and you all know that gold is chemically quite inert, which is the reason why we use it so much in plasmonics. But if you make gold nanoparticles and you put them on a titanium dioxide surface, and you investigate whether or not they catalyze the oxidation of carbon monoxide to CO2, which is one of the most important catalytic reactions taking place in the three-way catalyst converter of any car, then you will find the following. As you would expect for gold being chemically inert, down to a particle size on the order of about 4 nanometers, this material is catalytically dead. It does not catalyze the reaction. But then, as you can see, all of a sudden you have the onset of reactivity, which peaks around 3 nanometer and then goes down again. But you also notice when you look at the STM image that they take of the particles they used for this study, they are obviously not homogeneous. And what does that translate into? Well, it translates into this error bar along the size axis. And if we now were able to look at one of these at a time, essentially we would be able to see beyond this error bar, and we might find that there is a specific size where the activity might be a lot higher than what we actually see in that graph. So that's one reason why it is important to attempt to study nanoparticles one at a time. Now, if we project that more into the field of nanophotonics and plasmonics, which is the topic of this conference, of course, people have tried and successfully used single nanoparticles as plasmonic sensors, as in this seminal work from the Van Dyne group from 2003. And why would you do this? Well, because it's the ultimate level of miniaturization for a nanoparticle-based sensor. You cannot make it any smaller than using 1 nanoparticle if the nanoparticle is your sensor. You really minimize the sample volume that you need to create a signal, and it brings the dream, which now is maybe no longer a dream really, of label-free single molecule detection closer to reality. And I think this was the driver of a lot of work that has been going on in the field since. And there is numerous examples where one actually has succeeded to use a single plasmonic nanoparticle sensor to detect single molecules, as very nicely reviewed in this recent paper in ACS Sensors. Now, for us, we have a slightly different take on this and have kind of, in one of our recent works, combined these two aspects by using a single plasmonic nanoantenna as a probe to study how a single, in this case palladium, nanocrystal interacts with hydrogen. Now I will spare you the details why we want to do this and why this is interesting, but instead just focus on one of the key aspects to motivate the approach as such. So the idea is that palladium nanocrystals, they absorb hydrogen. At a certain hydrogen pressure, they form a hydride phase. This induces a shift of the scattering spectrum, which we can detect, and then we can, if we can make such dimers, we can look at how size and shape of these nanocrystals affects this process. And in essence, what we find in this quite busy graph is if you plot as a function of the side length of the single crystalline nanocube, the pressure at which they absorb a lot of hydrogen, that even for nanoparticles, which essentially have exactly the same size, that pressure can be up to 40 millibars different. Now you can ask, why is that? We believe it's related to the defect structure in the nanoparticle, but what I'm trying to say is that you would not find that if you would not look them one at a time, because then what you would see is what is illustrated here by the shaded red area, which basically is the error bar from the corresponding ensemble measurement. So indeed, you can see beyond error bars, and you will find that nanoparticles are individuals with their own personalities. And that can explain this with the concert analogy. If you are Freddie Mercury here, standing on stage, and you are looking out into the crowd of a stadium, as you play your music, you will see people, and they're all waving their hands and they're dancing, but you cannot really tell the difference, right? But if you take a close look at the front row, you will see, oh, some of them have long hair, short hair, different hair color, long nose, short nose, and they might actually also respond differently to the stimulus of your music, just like a nanoparticle. But I think it's clear now that it is important to look at nanoparticles one at a time. Let's be fair, there is many experimental methods to do that, electron microscopy, X-ray diffraction techniques that can do that, but I believe there is still one essential thing missing in this context. And that is, we are not able to control the mass transport of molecules to and from single nanoparticles while we are studying them. And if we project this statement onto nanoplasmonic sensing, there is a number of reasons why this would be very desirable. The first one, as you all know, that if you use a plasmonic antenna as a sensor, it is not uniformly sensitive. Essentially, as shown here by these blue dots, if you bind a molecule to these positions, it's only here in the hotspot where you actually generate a signal. So if you are interested in detecting single molecules, if your molecule binds here, you cannot see it, even though your sensor in principle would have the sensitivity if it would bind here. So it would be fantastic if we could direct the flow of analyte directly to the hotspot and to the hotspot only. So this is one reason. And the second one is that this becomes extremely important if you want to do sensing at low concentrations, where the time it takes for a molecule to travel to the binding site is essentially defined by diffusion, which makes it unrealistic experiments because you may have to wait forever, which is why it would be very desirable to force molecules to go there where they can be detected. And this is basically some of the motivation behind why we have started looking at integrating nanofluidics with single particle plasmonics in a way that is shown here. So what we're doing is we make nanofluidic channels and put nanoparticles into it. And in this way, we are enabled to control mass transport, as I will show you in the liquid and in the gas phase, to individual nanoparticles, but also away from individual nanoparticles. Interestingly, the flow profile in these nanofluidic systems is typically of laminar nature, so we have very well controlled mass transport. And as you can see already from this picture, this is compatible with well-established single particle plasmonic sensing strategies like dark field scattering spectroscopy. So you can nicely resolve the scattering spectrum of a single gold nanoparticle located in this nanofluidic channel, which here is highlighted, and it's not the background scattering from the walls. This you can suppress. So the question is this the or one of the missing links to ultimately enable fully integrated plasmonic lab-on-a-chip devices? So let's now get a bit more specific and look at how such a typical device that we make could look like. In essence, it's comprised of a microfluidic system connected, or two microfluidic systems connected by the nanofluidic channels, which in turn are decorated by nanoparticles. This is how a dark field image looks like. You can very nicely see the individual particles by the naked eye. Here we have again not taken any measures to suppress the scattering from the channel walls to make the channels actually visible. Then we can place nanoparticles of controlled size and also shape in these channels, and as you would expect on an open surface, if you increase the size of the particle, you will redshift your resonance. So nothing strange there just because we place them in these tiny structures. So what do we control here? We control, of course, the microfluidic system, the nanoparticle size, the nanoparticle shape, the composition of the nanoparticles. They could very well be more complicated than just a simple gold disc. The nanochannel dimensions in 3D, typically a few hundred nanometers or below 100 nanometers if we want to in 2 dimensions, and then at the micrometer scale in this dimension. And we control also the particle position in the channel. So how do we make such structures? Before I explain you that, I would like to pin down a couple of requirements that we have for this to work for our purpose. The first one, of course, we need a transparent lid, otherwise we can't do spectroscopy in the visible range. It should be biocompatible materials. We need very good sealing between the lid and the channel structures, because leaks will basically make the device unfunctional. We need high precision alignment to be able to place the particles in the channels. We want this to be chemically inert, and for catalysis, we also want it to be high temperature compatible. So this is quite a number of requirements that we have to fulfill. So how do we do it? Well, we start out with a silicon wafer, which is thermally oxidized to have a few hundred nanometer thick oxide layer on the surface. And then we define the nanochannels in a resist by means of electron beam lithography. We transfer the structures into the thermal oxide by means of reactive ion etching, which allows us to craft features with a feature size of around 30 nanometers. In the next step, we define the microfluidic system, which we need to connect this to the macroscopic world. And the strategy is pretty much the same, so we define them in a resist, this time using photo or laser lithography, because the structures are much larger. We don't need the resolution of electron beam lithography. And then again, we transfer the structures now down into the silicon by means of reactive ion etching or cryogenic etching. Then, in the next step, we fabricate the nanoparticles in the predefined channels. To do this, we write arrays of systematically shifted, and that is important, sensor particles in the resist with EBL. We grow them, do the liftoff, and then using SEM, we identify which of these particles, which all are slightly shifted, has the best alignment with the channel. We apply E-beam again to protect the best aligned particle with resist, to allow us to then remove all the misaligned particles as well as these markers and so on by wet chemical etching, leaving us, if we want to, with a single nanoparticle which is perfectly aligned with the nanochannel. In the last step, it's time to seal the whole thing. So we have a borosilicate glass lid into which we have to drill some holes in order to access the microfluidic system. We do this by sandblasting. After that, we have to very, very thoroughly clean this because any dirt will basically destroy the seal here. We activate the two surfaces by means of oxygen plasma, pre-bond them by simply joining them, and then apply fusion bonding at 550 centigrades for 5 hours to create a tight seal, and eventually dice the wafer into individual chips, which could look like this. What you see here with the naked eye is the microfluidic system, and the nanofluidics would be located down here. So, with this system at hand, What do you do? Well, you start out with the most simple kind of characterization to get to know what you have created. And what would that be for a plasmonic sensing structure? Well, it's to measure the bulk refractive index sensitivity. But before we do that experimentally, I think it's instructive to look at some FDTD simulations of this system. Because what I essentially want to show you is, as you change the width of the nanochannel, which is indicated here by these white lines, you are able to exclude or to occupy some of the sensing volume, which is defined by the enhanced near field, by the channel walls. So what you would expect is, if you make your channel smaller and smaller, you will decrease the bulk refractive index sensitivity because some of the sensing volume is already occupied by the walls. And this is exactly what you see in the simulations here for an 80 nanometer particle as we increase the width of the nanochannel. So then we designed the chip to enable experimentally assessing this problem, where we have 6 channels with 4 different widths, decorated with 4 nanoparticles of 4 different sizes. Here I then plot the peak shift we measure for these particles as we exchange the liquid in the channel from water to ethylene glycol for the different channel widths, and you see that there is some sort of linear dependence, which is in very good agreement with our simulations for the range of channel widths that we have considered in the experiment. So what do we learn from this? Well, we are indeed able to confine the fluid flow to within the sensing volume of a single plasmonic nanoantenna sensor. What more can you do? Well, because we now control the flow of fluid to and from particles, we can implement on-chip referencing in the following way. We have this chip design, 2 microfluidic systems, one filled with water, one filled with ethylene glycol, and by applying pressure on either of the microfluidic systems, we can either push water through in this direction or ethylene glycol push ethylene glycol through the other way. Then we have, I think it's 6 particles which are located in channels which are connected to both sides, and 1 channel which is only connected to the water reservoir. What does this mean? Well, it means a couple of things. First of all, we can now image these particles in the channel on our CCD chip. Note that we use monochromatic laser illumination, not through the objective, so we are here not going to measure peak shifts, but we're just looking at intensity changes in the scattering at the specific wavelength. And we have our 6 sensor particles and the reference particle in this channel. Now, if we just measure the scattering intensity as a function of time from one of these particles, you will see that there is some fluctuations which mainly stem from the light source, which is not perfectly stable over time. But if we now divide the signal from this particle by the reference, we get this very flat baseline here for a time span of about 13 minutes. Now, why is this interesting? It's interesting for a number of reasons. One, that if you now, in the next step, want to do a sensing experiment, you can keep your reference on the chip immersed in your solvent, but you will never expose it to the analyte, because if you flow your analyte this way, this will not be immersed in analyte because you also have a flow in this direction, so you will never have any back diffusion. So we have an on-chip reference in the same medium as the one you do your experiment. And you get this very flat baseline despite using a simple, cheap helium neon laser for illumination. You can do the first simple experiment, again exchanging the fluid and doing the refractive index sensing, where you get this very nice and smooth response, perfectly reversible, with the highest signal actually stemming from a particle where that does not resonate at the laser wavelength, but where the laser wavelength coincides with the flank of the particle, as you would expect. So what are the key features of these experiments? What do we learn? Well, we can use monochromatic excitation and readout, which is very interesting if you want to do multiplexing and look at many particles at the same time in their individual fluidic systems, because you don't have to, for example, employ hyperspectral imaging. We have this on-chip reference, which provides a very flat baseline over long periods of time, and the reference particle is essentially immersed in the same solvent at all times, which is a significant advantage if you want to do sensing. This is what we have done in the next step in a very simple proof of principle type experiment where we expose a single nanoparticle, a gold disc in a nanochannel to a thiol solution, and indeed we are able to detect the binding kinetics, which is actually quite fast for being a thiol, which says something about the mass transport aspect of the whole thing. But other than that, for the moment, let's just say this is a proof of concept that we can detect molecular binding to the nanoparticle. It's not more, but it's also not less. And we are right now working on applying this on a real biorecognition process, as well as we are hard at work trying to elucidate really to what extent can we overcome diffusion. How much faster can we detect molecules due to the fact that they are flushed by the sensor within just a few nanometers from the sensor surface. And I hope at a future occasion I will be able to tell you about what the outcome of this study was. For the last part of my talk, I will now switch topic a little bit and tell you about how we apply the same kind of system for single particle catalysis. Now, again, let's ask ourselves, why would you want to do that? Well, in essence, it's pretty much the same, because it will allow us to control the flow of reactant molecules to one single and very specific catalyst nanoparticle only. And if we know something about its structure, we can create structure-function correlations. Now, very importantly, we are not only controlling the mass transport to the nanoparticle, but also we can collect any product that is formed on this specific nanoparticle only, making sure that the product is not diluted in 3 dimensions, and for that reason becoming even harder to detect. So the question is, does this collection of the products from a single nanoparticle allow us to eventually quantitatively analyze it somewhere downstream? And use the plasmonic fingerprint of our catalyst particle, for example, to in operando measure the oxidation state of the particle as reaction happens, or a change in its geometry due to a surface reconstruction, and so forth. So this is the idea. Now, of course, it's easy to draw this idea in this kind of artist's view manner. It's also relatively straightforward to then translate this into a drawing on the computer, and this was our solution, what we wanted to build. We need a mass spectrometer to analyze the product, which is mounted on an ultra-high vacuum chamber, connected to a customized holder where we mount our nanofluidic chip. We have an optical microscope and some mass flow controllers and pressure gauges to control the gas flow, not liquid in this case, through our fluidic system mounted here. It took some time to translate this into something real, but this is how the setup looks like these days in our lab. Most important maybe here to discuss the chip design, which is now slightly different and looks like this. So we have 2 microfluidic systems, one U-type loop at the inlet, where we supply the gases at up to several bars pressure, the nanofluidic system here, and then the outlet microfluidics, which are connected to the ultra-high vacuum system and the mass spectrometer. If we zoom in, we have a second microfluidic system with much smaller dimensions, microfluidic channels that lead to 6 funnel-type structures, where we, in the center here, have our nanochannels, which are decorated by 1 or several nanoparticles. We can then measure the dark field scattering image. Here you can hopefully see the signature of some particles in the channel, and for example, in this case, obtain the scattering spectra of 4 copper nanoparticles with slightly different size inside this nanochannel. Let me now highlight again, this is constructed for operation in gas phase, not with liquids. If we want to do catalysis and run reactions, we also need to control temperature. So on the backside of our chip, we have implemented a resistive heater with the following features. It is supposed to and does mainly heat the nanochannel zone. Because of the small size of all this, we have very fast temporal response. We are also able to measure the temperature accurately by means of this resistive platinum thermometer structure, which is also grown on the backside of the chip. And we can reach a maximum temperature of about 350 degrees. So let's now see what this can do for us, and I'd like to explain this with the first quite simple example on the oxidation of copper nanoparticles. Why copper? Well, copper is an interesting material as it catalyzes a number of very interesting reactions. And it is also nice in the sense that as copper is metallic, it has a strong plasmonic resonance with a distinct scattering peak, but as it transforms into an oxide, you basically lose that signature completely. So you have a very strong optical signature for the transition between the oxidized and the reduced state. And then to start with, you can do the following experiment. We have these 4 nanoparticles in the channel with slightly different sizes. We start with them being in the oxidized state, and we apply 4% hydrogen and argon at 250 degrees to follow in real time how they are reduced back to the metallic state. And this is a video of the spectral response as a function of time here. And you will notice a couple of things. First, it will take some time to actually get the process started. And then you will also notice this wealth of features that appear, peaks appear here from the, let me play it again, if I manage, yes. From the long wavelength side, they appear, they disappear. But most importantly, you notice that the 4 different particles behave very differently. In both in time, when they respond, and also in which way they respond, which is another very strong indication that they are, of course, different individuals, right? It's not mainly attributed to the size because they are too similar for that. So having established this, we can now do our first catalytic reaction study by using the following chip design. You recognize this. I have shown this already, but this is this funnel structure which leads down to the nanochannel. Now, the challenge is, and what is unknown to us still, how many nanoparticles do we need in order to be able to detect a signal with our mass spectrometer? You can do calculations, and what you will find out is it's about the same order of magnitude. And the dream is, of course, to have 1. But we wanted to be in the safe side and started out by decorating not just the nanochannel, but also this funnel here with an array of nanoparticles that would look like this, so that we have about 20,000 particles in our system. But I can tell you that already now we know that we can reduce that to down to 200. But I will not show that today. They have 100 nanometer diameter, 30 nanometer thick, and made from copper. And then in the nanochannel here, we have the individual particles which are separated such that we can look at them individually by dark field scattering spectroscopy. And then we do the following experiment. We heat our chip to 300 degrees, apply 2 bars of 4% reactants in argon carrier gas on one side, and now we want to study the reaction of carbon monoxide with oxygen to form CO2, which is catalyzed by copper nanoparticles. We get 4 readouts, 3 from the mass spectrometer, 1 corresponding to the carbon monoxide and oxygen reactant supplied. And as you can see, we keep the carbon monoxide nominally constant and increase the oxygen concentration in steps. And then we measure the product formed. And what you see is the following things. Well, as we start to supply oxygen, indeed, we can measure the product formation. But you can also see that we don't measure any oxygen until a certain critical point, which means up to here, we are completely consuming the reactant, oxygen, which is in deficit here, to the formation of carbon dioxide. And then you notice that at a certain oxygen concentration, we start to see oxygen coming out, and at the same time, we start to see a distinct decrease in the activity of the catalyst. And if we now look at the optical signature of the 4 particles in the channel, this happens when they undergo the transition from the metallic state to the oxidized state. What does this tell us? Well, it tells us that, as we've known in beforehand for this particular system, the metallic copper is the much better catalyst for CO oxidation than copper oxide. But it also tells us that we are able to operate this reactor in a completely mass-transported limited regime. And most interestingly, if we have a close look here, we will see that there is a time delay in the switching from the metallic state to the oxidized state for these particles. And this becomes very clear in this picture as we zoom in, where you can see that the time delay is substantial. And you can ask yourself, why is that so? Is it the size dependence of the oxidation kinetics of copper? As I said, I don't think so, because these particles have almost the same size, and in fact, the transition occurs at the same time scale. There is just a delay for when it starts, which I believe, and I find this very exciting, is the fingerprint of a completely mass-transported, limited oxidation process inside the channel, which means that we supply, due to the small dimensions of the structure, so little oxygen that it is all consumed by the first particle, the black one, which is the one upstream where the reactants reach first. And only when this has been oxidized completely and doesn't consume oxygen anymore, the second one downstream starts, and then the third one, and then the fourth one. So this is indeed an illustration that we are able to run our reaction in the completely mass transport limited regime and can control that by the dimensions of our channel. And why is this important? And this is my last slide. Well, because a real catalyst, for example, the three-way catalyst in the car, is comprised of a mesoporous support where the active particles sit inside small pores which control the mass transport of reactants to and from the catalyst particles. Which means that mass transport through these pores essentially dictates the behavior of the catalyst. And it also means if you probe such systems in the conventional way, you will probe a mess of catalyst particles operated in very different regimes depending on where they sit inside a pore. And our nanoreactor, as we call it in this context, may now constitute a platform to study mass transport effects in catalysis at the single nanoparticle level. With this, I'd like to sum up, and what I've shown you is that we have constructed a nanofluidic device for controlling mass transport to individual nanoparticles. We can do single particle dark field scattering spectroscopy and sensing, on-chip referencing, parallel sensing of several individual nanoparticles and nanochannels, and we can detect molecular binding events. For the single particle catalysis application, we have created a nanoreactor with integrated heater. Again, we can do dark field scattering of single particles and combine that with mass spectrometry. We can, in operando, monitor the catalyst oxidation state at the single particle level and correlate, for example, the oxidation state with the activity of the catalyst, and we are able to reach a regime where we can control mass transport and what conditions the reaction occurs at the single nanoparticle level. With this, I'd like to thank, first of all, my fantastic single particle team, which has grown quite a bit the last year, all the collaborators that are in one or the other way contributing to these efforts, and all of you for your attention. Thank you.
Any questions for Christoph?
It's more a technical question. So for these really tiny...
Wait for the mic.
Okay, so it's
yes.
a more technical question. So, but these really tiny microfluidic channels, which are in the range of hundreds of nanometers or something like that. So it's for me really hard to understand what kind of pressure difference you would need between your two reservoirs to really get a flow of a fluid through these really tiny channels. And what is there no problem with the surface tension of, let's say, if you use the water in these really tiny capillarities?
So this is, of course, a very interesting question. And for the liquid phase, this has been relatively well known because people have been using nanofluidics in different contexts, right? I will get back to the specific answer. For the gas phase, we had no idea. So we had to just start somewhere. And it turns out that, well, you apply 1 atmosphere on one side, but then on the other side, we happen to have 10 to the minus 10 millibars. But that's what the mass spec requires. So I cannot really answer what pressure difference we have to apply for there to still be a flow. But at these conditions, the flow is actually very efficient. We were surprised by how much we get through per unit time. But we are still exploring that particular thing, so I cannot answer. For the liquid phase state, of course, it depends on the length of your nanofluidic channel. The longer you make it, the larger flow resistance you have. But typically, what you do, you apply a couple of bars of pressure on one side, on one of the microfluidic reservoirs to push the liquid through. Then what flow rates you get is something that is also not very well known, because it's very hard to measure, and we're actually having a tool here where we can do this. So that's one aspect, the fundamental nanofluidics aspect, that is also interesting that we are looking into.
Yeah?
Yeah, yeah, very impressive talk. Wanted to ask a question about addressing the problem of getting the analyte to the sensor by nanofluidics. Can you comment what type of concentrations you work with, in what concentrations range you can work with nanofluidics, and secondly, any ideas of further improving the sensitivity of the plasmonic system?
How to improve the sensitivity?
Okay, so again, two questions.
No, just the second one. How to improve the sensitivity?
Because, yeah, you showed reference measurements. So I'm wondering, are there any other ideas, different plasmonic particles, maybe, etc., just to get to single, right? If that's one of the dreams.
So when it comes to the concentrations, I think one thing I want to make very clear here is, of course, you cannot push whatever through these channels. You have to avoid that they clog, because they have these tiny dimensions. But I mean, for now, I have forgotten the actual concentration used in the Thiol experiment that I've shown. But the idea is to go down to micromolar, nanomolar, picomolar, and just see where does it stop. I mean, this is where do we no longer see, or do we ever see, a real benefit of applying this flow to the nanoparticle rather than letting diffusion do its job. We are in the midst of exploring that, and I cannot tell you. But the idea is, of course, that you can go to very low concentrations. The second question about increasing the sensitivity of the sensor, I mean, you can possibly, as long as you can integrate it with the fluidic structure, which mainly is a nanofabrication challenge. The more complicated structures you make, the more complicated you make an already reasonably complicated process. You can probably apply the entire toolbox that is known from nanoplasmonic sensing, making different shapes, nanorods rather than nanodiscs, single crystalline particles, dimers, whatnot. But it's complicating the system as such, which is why at this stage it's not really our priority, because we want to understand better what the system can do for us by keeping the particles as simple as possible.
So, because you mentioned in the beginning also about for the sensing part, for the single nanoparticles, can you imagine to, for instance, use like a pair of nanoparticles to generate more these hotspots, and then even go down with these kind of channels even more, really to address exactly these points? I mean, this could increase a lot your sensitivity, but it's probably very challenging. I don't know if this would be possible.
We are working on that, but it's to start with a nanofabrication challenge. But of course, that's the next level that one would like to take.
So would you really think one can go that much down? Yeah.
Yes. At the price, I mean, everything comes at the price, right? Then, I mean, your channel dimensions become extremely small. The flow in terms of molecules per second that pass through such a constriction will be very, very small. You will face other challenges, but yes, we are confident that in one or the other way, we have some very concrete ideas that we should be able to fabricate such structures, yes.
More questions? I have one. So, since all your particles are different, and if you want to do any quantitative sensing experiments to link your signal to the concentrations, it means that you have to calibrate each of your particles separately.
Yes, probably.
Okay. So, I mean, is there a really advantage compared to ensemble?
Well, it depends what you want to detect. But if what you're after is detecting a specific binding event of a single molecule, this will give you a stepwise response.
So if you want just detections, then it's no problem. But if you want to link your step to some kind of concentration in your solution.
Well, as long as it's a step and you know where the step comes from, even if the step size is different, you still know that what causes the step. But if you want to deconvolute, if the step is it corresponds to binding of 1, 2, 3, or 4 molecules, well, you are absolutely right. Then you would have to, in one way or the other, calibrate your sensor. Now, I'm not sure, because we have not looked into this, and I'm not sure if anyone else has, how relevant this single particle personality thing is for this type of sensing. There is cases where this might not be so relevant. It might be more important where exactly in the hotspot your analytes bind, for example. But this is something that one potentially also can look into using that platform, and it might be very important, or it might turn out to not be as critical. So how important these single particle personality things are depend very much on the specific case.
Any more questions? So if that's not the case, we can take the coffee break. And we start at 10:45. Yeah.